In this lesson, we're going to talk about shift registers and what shift registers do for digital circuits. For the most part, what shift registers are used for is to manipulate data, whether we're going to move data in and buffer it or store it, whether we're going to move it around shifting left or right, bringing data in one bit at a time and storing it and bringing it out in parallel. All those kinds of modes are used for shift registers. Now let me show you the different types of shift registers we have. The two types that are kind of related to each other are serial in and serial out. And they're either a shift right or a shift left. So you can see here data comes in here and it comes out of here. The shift left goes in from the left and comes out from the left. So we can move data to the right, we can move data to the left. Another type is a serial in, parallel out. In other words, you may shift in one bit at a time in serial format, and then once it fills up with all 8 bits, you unload it all 8 bits at a time. So you can shift in 1 bit at a time and shift out 8 bits at a time. You see this a lot if you've ever seen these LED cubes, these LED matrices, which the LEDs are in a matrix that light up and show things on the screen. Those are generally sent in 1 bit at a time, and then they're unloaded 8 bits or 16 bits or whatever at a time. The reason they do that is because we only have to use one data output pin instead of 8 data output pins. So this is a really good way to make efficient use of smaller amounts of output pins on a microprocessor. Another format is the parallel in serial out, where you have 8 lines in and you'll have 1 going out. A good example of this is like your modem. If you have a dial-up connection, which hardly anybody does anymore, but if you did, they used a process similar to this where it would bring in parallel data from the computer and send it out 1 bit at a time while modulating it for the telephone line. So you have 8 bits in and 1 bit out, and this was the receiving end. You got 1 bit in from the telephone line, and that would store up and then send out 8 bits into the computer. So these are kind of related to the UART inside your serial port in your computer. The parallel in, parallel out, this is mostly used for storage of data. You can kind of picture this as memory banks inside your computer. You send 8 bits of data into it and it stores it up until you need it. So it's a really good way to send information but buffer it between the input and output. And this is what's called a universal, and you can either shift in and out, right or left, either way. You can also do parallel in, serial out, serial in, parallel out, serial in, parallel out, and serial out, whatever way you want to do it. So this is kind of the universal processor. So let's look at the waveform. And the waveforms for these they're pretty straightforward. You see that the J and the K are, for the first one, are tied open. And then you see the Q is tied to J, the Q naughts are tied to K, Q to J, Q naught to K, on and on. And the outputs that we're going to draw are actually from the Qs. And then we have, in this case, we've got the sets all tied high, and we've got the reset actually going to the reset lines of the clear lines of the processors. So let's start this out. We give it a reset pulse, and a reset pulse is going to make Q go low. So we're going to start out all lows on all of these. And for this one, we're going to say the data line, I'm just going to tie that high, and I'm just going to leave it as a high. It's really not practical for anything, but just to show you how data moves, let's tie it as a high all the time. We can kind of ignore the K's, just do what's on J and ignore K, kind of like use it as a D-type flip-flop, and it's a lot easier to understand. It's positive edge triggered, so it's going to be every positive edge, so let's go and highlight this, and you can go ahead and do all the positive edges all the way down for these, since the clock is tied to all of them. They're all going to change at the same time. So all the positive edges. And this first one, it sees a high on J, so we're going to set that flip-flop. And it's going to stay set all the way over to the next input. This one, to figure out what's going on with this one, it's actually looking back at Q0 for the previous one. But if you look right here, it almost looks like it's a high. But remember, propagation delay, even though Q0 looks like it's here, it's really not changing. If this was the clock, in reality, it's not changing until 20 nanoseconds later. There's a gap there. So what we need to do for this one is kind of look back at what it was previously. And if it was low previously, we're just going to stay low there. This one's going to be low, and it's going to look back and see it as a low previously, so it's going to stay low. This one's going to look back and see a low, so it's going to stay low. So unlike the counter circuits where we could do this one all the way across and then we could do the next one all the way across, this one you kind of have to go clock by clock and figure out what's going on. Okay, for Q0 again, we're tied high here for the data. And honestly, for this one, since it's high all the time, we can just say that this is always going to be high. We're not changing our data, so in reality, it's never going to change. For this one now, we look back and it sees it as a high, so now it can go high. In other words, we're going to set those flip-flops. And since it's always high, we could just transfer it all the way out. Since it's always looking back and seeing a high, it's never going to change. We could just say it's high all the way across. This one looks back and sees a low, so it's going to stay low. And this one looks back and sees a low, so it's going to stay low. This one looks back now and sees a high, so it's going to go high, and it's going to stay high because it always sees a high all the way across. And this one sees, if you look back, sees a low, and then it looks back and sees a high, and it looks back and sees a high, looks back and sees a high. So really, this one didn't do a whole lot. Like I said, it's just for showing you kind of how data moves. But if we were to draw this out with a Q0, 1, 2, and 3, it starts out at all lows. My data line, my data input is a 1. So the 1 is getting like pushed in from the end. So we got a 1 there. This 0 now becomes that place. This 0 moves over there, and this 0 moves over here. 1 gets pushed in again. This 1 moves over there. That 0 moves there, and that 0 moves there. 1 gets pushed in. This 1 gets pushed there. This 1 gets pushed there. This 0 gets pushed there. 1 gets pushed in. 1 goes there. 1 goes there. 1 goes there. And then we're just shifting 1s in forever. So you can see it kind of pushes that 1 in one section at a time, just one spot at a time. It kind of picture a tube of some kind, and you're pushing a ball of some kind in, like a white ping pong ball into that tube. It's going to slowly fill up that tube with the white ping pong balls. So let's look at a more practical example of the shift register. This particular one is called a ring counter. And the reason it's called that is if you look at Q goes back here and goes to J, and also Q naught goes to K. So it's a ring. In other words, it's a full circle. Sometimes you'll see these as recirculating counters, shift registers. So got a couple different names, but a ring counter is what we'll call them. And for this one, you'll notice that the clock's going to all of them. Q goes to J on each one of these, so there's no inversion or anything like that. Clock goes to all of them. But you'll notice this reset line, the reset line goes up here to where it goes to set, reset, reset, reset. So in reality, Q0, since we're setting the first one, it's going to start high. The other ones are going to be reset, so they're going to start low. So since this reset line right here is going to the set line, we're going to start out at set, reset, reset, reset. So high, low, low, low. Positive edges, so we can go highlight all our positive edges here all the way down, since the clock's tied to all of them. Okay. Now for the first one, J is actually going to look back at the Q3 output. So you can see it's tied back. So what Q0 is going to do, it's going to look back and see what Q3 is doing. Well, Q3 is low, so Q0 is going to go low. It's going to look right here, right before the clock. This one looks back and sees a high, so it's going to go high. This one looks back and sees a low, so it's going to stay low. And this one looks back and sees a low, so it's going to stay low. This one looks back again to right here, and it sees a low, so it's going to stay low. This one looks back and sees a low, so it's going to go low. This one looks back and sees a high, so it's going to go high. And this one looks back and sees a low, so it stays low. So you're always just looking back right before that clock happened. This one looks back here, sees a low, so it's going to stay low. This one looks back and sees a low, so it stays low. This one looks back and sees a low, so it goes low. And this one looks back and sees a high, so now it's going to go high. This one looks back, sees a high, so it goes high. This one sees a low. This one sees a low. And this one will go low because it sees a low. Looks back and sees a low, so it goes low. Sees a high. Sees a low. Sees a low. And this one sees a low. Sees a low. Sees a high. And sees a low. So you can kind of see the stair-step pattern going on here. It's kind of steps down for each one. If we were to draw those out, 0, 1, 2, and 3, we start out with 1, 0, 0, 0. Right? Set, reset, reset, reset. Take this 0 on Q3 and move it over here. That 1 now moves over to 1. 0 moves there. 0 moves there. This 0 gets pushed there. That 0 goes there. That 1 goes there. And the 0 goes there. So it just moves everything over. Again, like taking a ping pong ball in a tube and pushing it in one end and pushes everything over. Take this one out and put it here. That one goes there. That one goes there. That 1 goes here. 1 moves over to here. 0 goes there. 0 goes there. 0 goes there. So this one you could say it's shifting right. So it's moving everything to the right. It's going this way. So it's going to the right. If we were to flip these over and say 3, 2, 1, 0, it would be shifting it to the left. There really is no most significant, least significant bit in shift registers. It just depends on how you take your output. Depends on if it's shift right or shift left. There is no most or least significant. Okay, let's look at another one. And again, you can pause this or rewind it if you need to, but let's look at the next one. This particular one, you'll notice that we've got a J, but the J is now feeding back to Q0. This one's what's called a twisted wing. Because the ring has been twisted, so it's a twisted ring counter. Okay, so we can get our reset lines, and they're all going to the reset signal, so they're all going to start low. And let's highlight our, in this case, positive edges. Give you enough of an idea of where to change. Okay. And so the first one, again, it's looking back, but it's looking back at the inverse of Q3. So it's looking at the opposite of Q3. So if we look back here, Q3 is low, but it's going to like run it through an inverter, right, and go to there. So instead of it seeing a low, it's actually going to see it as a high. This one looks back and sees a low. This one looks back and sees a low. And this one looks back and sees a low. So the only one affected is that Q0 to Q3. So Q0 looks back, it's low, Q3 is low, but it sees it as a high because it sees it through an inverter. This one now sees a high, so it goes high. This one still sees a low, and this one still sees a low. This one looks back again, that low is inverted to a high. This sees a high. This now sees a high, and this sees a low still. Remember to look back right before the clock. This looks back, it's low, so it sees it as a high. This still sees a high. This still sees a high. Now this one sees a high. Q0 looks back at Q3. Now it's high, so it's going to inverse. It's going to see it as a low. So now it's going to go low. High, high, high. This looks back at a high, so it sees it as a low. Now that sees a low. This sees a high still. And this one still sees a high. So again, just look back each one. Q0 is going to see the opposite of Q3. So if it's high, it's going to see it as a low. And if you do mess up, the best way to do is erase the whole thing and redo it, because it's really hard to kind of find where you were out in the middle. So I recommend you just go all the way back to the beginning if you think you messed up. Start this out, it's all zeros. But now remember, Q3 is inverted, so the 0 comes back to a 1 and everything else shifts over. 0 becomes a 1, everything shifts over. 0 becomes a 1, everything shifts over. 0 becomes a 1, everything shifts over. Now this 1 becomes a 0, and still things are shifting over. 0, 0, 1, 1. and on and on. So this thing basically fills up with ones, fills up with zeros, fills up with ones, fills up with zeros, fills up with ones, fills up with zeros. This particular setup is also called a Johnson counter. Because of the layout of the outputs. When you start it, it's a twisted ring with all zeros to start. That is a Johnson counter. Not all twisted rings are Johnson counters, just the ones that start out that way. So now you could also do this with just how we've been doing it with the ones and zeros without having to deal with the waveforms, and I'll give you some of both. But what you need to do is figure out what it starts at. So we've got a reset, set, reset, and set, right? So this one goes reset, set, reset, set. So if you've got that situation, you're going to reset, set, set, because set, remember, always makes it high. This is a a regular ring counter, because Q goes back to J, so it's a regular ring. So whatever's on Q3 comes back to Q0, and everything else gets shifted over. So that goes in that box. That goes in that box. This 0 goes in that box. 0 comes back over here, and then that goes there. That moves over to there. That moves over there. This 1 goes here. That 0 goes there. 1 goes there. 0 goes there. And on and on and on. This basically repeats the pattern over and over and over again. What they use these for is, if you've ever seen marquee or twinkle lights, if you've ever seen it where they look like they're chasing lights, where they're chasing each other, that's basically what they're doing, is they're turning on every other every other light, and then flipping those and making the next set come on, and turning them off and on every other one. So it gives you this chasing light effect. Okay, let's look at another one. This one is going to be reset, 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 reset. So they're all start with zeros. This one, in this case, is a twisted ring, because we've got Q0 going to J, right? So it's a twisted ring. So whatever's on Q3 is inverted back to Q0. So that 0 goes back as a 1, inverted, and then that 0 gets moved there, that 0 gets moved there, that 0 goes there. Invert this to 1, 1 goes there, 0, 0. 0 gets inverted to a 1, 1 goes there, 1 goes there, and 0 goes there. 0 gets inverted to a 1, 1 goes there, 1 moves there, 1 moves there. Now this 1 gets inverted to a 0. These get shoved over. 1 goes into a 0. Everything gets pushed over. Oops. 1. 1 goes to a 0. 1 becomes a 0. That 0 becomes a 1. So you can see again, it fills up with ones, fills up with zeros, fills up with ones, fills up with zeros. Let's go on to the next one. And this one, same thing. So we've got reset, reset, set, set. So it's 0, 0, 1, 1, because we set those two. And it is a J goes to Q0, so it's a twisted ring. So this 1 now becomes a 0, and these 0, 0, 1. 1 becomes a 0, goes 0, 0, 0. 0 becomes a 1, 0, 0, 0. 0 becomes a 1, 1, 0, 0. 0 becomes a 1, 1, 0. 0 becomes a 1. 1 becomes a 0. Oops. Sorry. 1, 1. You can see that sometimes I get thrown off here. It's easy to do. And that becomes 0, 0, 0, 1. So this is just like the last one, except we started kind of in the middle before we did it. Okay, that's shift registers. If you have any questions or problems, rewatch the video, and this should cover everything you need to know that I'm